Good morning, students. So we are starting now. First, let me know if you can see the video and you can hear my voice. Then I will start. Okay. Okay, so let's start today's class. I will start with some of the questions I have received yesterday in the question and answer part. Okay, I think some of the questions I answered yesterday, I will still quickly try to reply some other questions. How was Neptune discovered? Means what was the process? Do we have to write? Okay. Of discovering Neptune. So what I was trying to tell was that the location of Uranus can be calculated using Newtonian mechanics. So when I say Newtonian mechanics, I am not just saying Newton's laws of motion. I am encompassing all the laws which are coming up eventually from Newton's law. So eventually, when the location of Uranus was calculated, the calculated position of Uranus found to be little bit different than the observed value. So there was a discrepancy, and in order to resolve this discrepancy, it was predicted that there might be another planet nearby. Now, because of the gravitational effect of the other planet, there is a shift in the position of the Uranus. So, in order to make Newtonian mechanics correct, the presence of another planet was predicted, and eventually it was found. So it is not just predicted, it was also observed that yes, indeed, there was another planet. Do we have to write notes? I think I told yesterday. Probably, since the video will be anyway available, so just concentrate on what I discuss, what I am discussing through the audio visual means. I think that will be better. How does the discovery of planet Neptune is related to STR? I think this I answered yesterday. It is not related to STR as such, but the discovery of planet Neptune is in fact establishing the correctness of Newtonian mechanics. So that was a very high point of Newtonian mechanics. Why Newton's laws are not adequate? So again, I discussed yesterday, we cannot say that Newtonian laws are inadequate in general. Actually, it will all depend on what is the speed of the frame of reference, or what are the relative speeds of the frame of reference. Again, why frame of reference is coming? Whenever you want to make a measurement, again, in physics, measurement simply doesn't mean that you are measuring the length of something or you are measuring the weight of something. It can be various other measurements. Any physical quantity need to be measured by doing an experiment. So I'm talking about all such measurements. Now, whenever you are performing an experiment to measure a quantity, it has to be with respect to a certain frame of reference. Now, if the frame of reference in which the measurement is made, or the frame of reference of the body on whose physical parameter you are measuring, if there is a relative motion, and the relative motion is comparable to the speed of light, only then the Newton's law will become inadequate. But other than that, in most of the cases, as we discussed yesterday, the velocity, the highest velocity we can think of will be much less than the velocity of light. So that way, in most of the cases that we see in our day-to-day life, Newtonian mechanics is adequate. And of course, you can still use relativistic mechanics that will only incorporate some accuracy. But Most of the cases, this much amount of accuracy is not needed. In fact, this much amount of accuracy you may not feel, or your measurement technique, your measurement tool will not be able to detect this much amount of accuracy. I hope that the part is clear. See, the relativistic mechanics, the importance of relativistic mechanics will be coming when the measurement is done in a frame on a body, when the relative motion of the frame of reference is comparable to the speed of light. There is another question: which device observes such objects which move with the speed of light? First of all, you know that with the speed of light, only the photon moves with the speed of light. So if you want to measure the speed of photon or the speed of light, then the simplest way to measure the speed will be probably you allow light to go from one place to the other, and then you start a clock when the light starts and you stop the clock when the light arrives, and then by knowing the distance and by dividing the distance by time, you will be able to find out the speed. For example, let me send a beam of light from here to the surface of moon, and let me place a mirror on the surface of moon. So light will get reflected from the surface of moon and it will come back. I will start a clock when I switch on the beam, and I will stop the clock when the beam will arrive on the detector, which is on my Earth. So knowing the distance from Earth to moon, I will be able to find out the speed of light. So this is, of course, this is not just only way, but maybe the simplest way. Then yesterday there was, I missed when I was taking one example of a supersonic jet which was moving at 1200 km per hour. In my calculation, actually, I used 1200 km per second. So actually, it should be 1200 km divided by 3600 meter per second. Okay, so I have corrected it in the next class, but this is for your record that that particular unit need to be corrected. Is it related with Lagrangian mechanics as well? I think I mentioned yesterday that Lagrangian mechanics is one form of Newtonian mechanics. So whatever inadequacy, Newtonian mechanics will have the same, Lagrangian mechanics will also have. By laws of physics in an inertial frame, do you mean by only Newtonian laws? Actually, before maybe 1900 or so, I mean, at least during first 150 years since the Newton wrote his famous Principia of Mathematica, the universe, the physical phenomenon in the universe were mostly explained by Newton's law or some derivative of Newton's law. So classical mechanics was almost entirely governed by Newton's law. So it was only later, starting with Maxwell's equation, and then after the entry of Einstein, that we started understanding that Newtonian laws are not enough. So when I say what are the laws of physics, then mostly it will be Newton's law or derivative or of Newton's law, maybe till the first 200 years, and slowly the other laws have been established. Can a frame of reference be relative from person to person? So actually, when we make a measurement, we will ensure that our measurement is remaining static, probably with respect to the ground. So even though I am making a measurement, I make sure that my measurement tool is steady, or even if it is moving, it is not moving with a very high speed. Similarly, if another person is making a measurement, it's most likely that the measurement is made on the ground, or if it is on a moving stage, then the stage is not moving with something comparable to the speed of light. So in these cases, we will not bother about the relative motion of the frame of reference. So in that case, we'll consider that even though there are two persons, strictly speaking, you may say if one person is moving, then he can have a different frame of reference attached to his body, but its effect will be negligible. So in such cases, we normally do not bother about the relative motion. Then, does an inertial frame of reference actually exist, or is it something which cannot be identified relatively? I think this is a very interesting question and important question as well. What is an inertial frame? So I define an inertial frame as a frame where the laws of physics will be valid. So that is the definition, but telling which frame is an inertial frame is not so easy, because how do you know? In order to validate that, you have to see that in a given frame all laws of physics are correct. And on Earth, probably we may try to think that it is an inertial frame because most of the experiments we are doing on Earth. But then Earth is having its own rotation about its axis. So even if we consider that revolution around the sun is at a constant speed, but there is a rotation also. So strictly speaking, even the measurement taken on Earth will be with respect to a frame of reference, which is not actually an inertial frame. But for most of the cases, because if we are making a measurement, we will be mostly making the measurement on Earth only. So many times we consider that whatever we are doing on Earth is on a frame of reference. Of course, there is a constant speed, but if we are making the measurement today at 9 o'clock and then I am comparing this result tomorrow at 9 o'clock, so I am at the same angular position today as well as tomorrow, so that I can probably ignore the change in the angular position. I need to bother about only the speed, and I will consider the speed to be constant. So that way I can consider to a certain extent that the measurement I am making is on an inertial frame. But it is very true that difficult to tell. First of all, you have to establish an inertial frame. Once you establish an inertial frame, with respect to that inertial frame, you can tell which is the other inertial frame, because any other frame which is moving with a constant velocity will be also an inertial frame. So the other question is, so STR is not always about speed of light. Actually, when we talk about special theory of relativity or theory of relativity, it is intricately related to the speed of light, because you have to consider the relative motion comparable to the speed of light. So speed of light is directly connected with the theory of relativity. Then here is another question. If a frame of reference is moving at uniform speed, it means that it was accelerated at some point to attain that velocity. Do we still consider it as unaccelerated frame of reference? So the question is, even if you are considering an unaccelerated frame of reference which is moving with a constant speed or constant velocity, but in order to attain that speed, it might have accelerated at some point of time. But for us, what is important, that when the measurement is done, whether that frame of reference is having a constant velocity or not. So if the frame of reference is having a constant velocity when you are making the measurement, then we'll consider that to be an inertial frame. Of course, the constant velocity with respect to another inertial frame. If the observer is in the accelerated frame and consider the measurement on an unaccelerated frame, then do we consider STR? So there is an accelerated frame and then there is an unaccelerated frame. So if you are looking at the consequence of measurement on two frames, one is accelerating, one is unaccelerating, then it will not come under special theory of relativity, because here at least one frame is accelerating. How is the discovery of planet Neptune related to STR? I think that is answered. Is kinetic energy also relativistic? Yes, you can see kinetic energy depends on mass and velocity, and velocity and mass we'll soon see are not constant across the frame of reference. So depending on which frame of reference you are making the measurement, the velocity or mass can vary. please give an example of unaccelerated frame of reference. So I gave the example that considering the ground to be an inertial frame, again, you see, most of the time we will consider the ground to be an inertial frame, but truly speaking, it is not an inertial frame because we know that it is rotating. But for our understanding, we'll consider the ground to be an inertial frame. Now, if there is a train which is moving at a constant speed, then the train will be an unaccelerated frame of reference. So here is another point. I think in the explanation yesterday, I showed that when I defined an inertial frame, a moving inertial frame, then I showed that the frame was moving in the positive x direction and with a constant speed. So many times I used constant speed, but you can see that the speed was in a given direction. So actually, the better, another way of telling is that the other frame of reference, the moving frame of reference, is moving with a constant velocity, so that you understand that the direction is not getting changed. So constant speed without changing the direction or constant velocity need to be that of the moving frame of reference. So with that, I think we'll move to the next part. So we'll start with a transformation called Galilean transformation. So what is a transformation? Actually, we are talking about the transformation of coordinate system pertaining to or of coordinate system. So a transformation will relate one set of coordinates with another set of coordinates. Now, one set of coordinate can be on a frame of reference which is at rest, and the second coordinate system can be a moving frame of reference. So it may correspond to a frame of reference which is moving with a constant velocity. So if we are talking about the transformation, so now, as I said, the relation between the coordinates of a event between the coordinates of an event in one frame of reference in terms of another frame of reference. The relation between the coordinates of an event. So there is one event taking place, and I describe the coordinate of that event in one frame of reference in terms of the coordinates of the same event in another frame of reference when the first frame is moving with a constant velocity with respect to the second frame. or vice versa. And when we do this, when we try to establish the relation between the coordinates of an event in one frame of reference one frame of reference at rest, for example, in terms of the coordinates in another frame of reference of the same event, when there is a relative motion and one of the frame is having a constant velocity. When we do it under classical physics regime, then the transformation is known as Galilean transformation. So here we consider coordinate transformation under classical physics regime. So we are considering classical physics, remember. So then only we'll move to relativistic mechanics. Now, what is the main assumption? Classical physics means we are mainly talking about the laws governed by Newtonian mechanics. Newtonian mechanics. What is the fundamental assumption when we describe the transformation equation? What is the fundamental assumption? The fundamental assumption is that the time is universal. Time is universal. So this is one very important assumption. What is meant by universality of time, which is the fundamental assumption in Newtonian mechanics? This means, let me consider that there are two frames of reference. One frame of reference S, which is at rest, and then there is another frame of reference S prime. S prime is moving with a velocity v. So I may define this x, maybe. Okay, so x. Normally I'll consider. Let me not use this. I'm just considering that this is my x or x prime axis. Okay, so the motion is taking place in the positive x direction, and by universality of time, what I am considering that, let us consider that there are two observers, one attached to frame S and one attached to frame S prime, and both are having their own clock. And suppose the two clocks are synchronized in such a way that when the frame S prime started at t equal to 0, at t equal to 0, S and S prime were having the same origin. At t equal to 0, S and S prime were coinciding. They were coinciding. So this part was here at t equal to 0, and they both had their own clock, and these clocks were synchronized at t equal to 0. So we have t prime equal to 0 when O and O prime were overlapped. But that is at the time t or t equal to 0 or t prime equal to 0. But after that, this frame started moving, so it is getting away along the x direction. Even then also, t will remain to be equal to t prime. So doesn't matter at what time an observation is made, the time as far as the two frames are concerned, it is the same time. Whether you are considering the clock of the observer on frame S prime or the clock in the frame S, the time is going to be the same. So that is meant by the universality of time. So with this assumption, so that is the fundamental assumption. Let us now try to establish the transformation equation. So let me consider that there is an event taking place at the location T, and S measured by the observer in the frame S prime. The location of the event is found to be X prime, Y prime, Z prime. And this event is taking place at time T. Time T or time T prime, now it doesn't matter since we know that T is equal to T prime. So the event is taking place, and the event, what constitutes an event? So something has happened. It can be, somebody has clapped. So the observer himself, he clapped at the location P. So that can be, or another person clapped at time T at the location P. That can be an event, or simply bursting of a firecracker. Bursting of a firecracker. So that is taking place at time T at the location X prime, Y prime, Z prime. But you know that this frame is moving with a velocity v. So at time T, the origin is now shifted by an amount v into t. What is X prime equal to? You may drop a perpendicular and you know that this length is equal to X prime, because it is the observation made in the frame S prime. That is the distance along the x-axis of the projection of P from the origin O prime. Now what is X? What is the location of the event P along the x-axis as made by frame S? So that will be this distance X. Now you know, sorry, this I have already written. This separation is Vp that I have already written. So it means that if I can write X prime is equal to X X minus Vp. And the frame is moving only in the X direction, so there is no relative motion along the Y or Z direction. So Y prime will be equal to Y, Z prime will be equal to Z. Of course, P prime equal to T. Now these sets of equations, these are called Galilean transformation. But here we consider that the frame of reference S prime is moving with a velocity v along the X direction. So this is not the most general expression. If you want to write down the most general expression, I'll have to consider that the frame S prime is moving with a constant velocity, but in any arbitrary direction, not necessarily along X. So the general expression, if I have to write, so let me consider that this is my frame S and this is the frame S prime and this is the frame S prime, and actually it is moving not necessarily along X direction, but so if I join these two origins, O and O prime, it is in some arbitrary direction. Now, in this case, suppose here is the event taking place at P. Now, the position vector of this, you can call it as, let's say, R prime, and the position vector of the same event in S prime frame will be R. And you know from here that R equal to, or you can define R prime vector equal to R vector minus V into T. So this distance is equal to Vt if I give the direction of the velocity. If I incorporate the direction of the velocity, then Vt will be another vector. So R prime equal to R minus Vt. This is the most general expression. Of course, T prime remains equal to T. So this is, let me give a number. This is the most popular form of the Galilean transformation. But if we want to make it more general, then 2 will be the more general expression of Galilean transformation. But in addition to this particular generalization, there can be further generalization. The further generalization can be, number one, that at t equal to 0, the two origins may not coincide. At t equal to 0, O and O prime may not coincide. They may not be at the same location. So there is already a separation between O and O prime. So that can be another generalization, but that will only add a constant factor. Then second generalization, in addition to that, the frame can rotate also. So S prime can rotate with respect to S. So this generalization can also be incorporated. Of course, we are not going into all these details, but for us actually, the generalization that the frame of reference S prime can be moving with a constant velocity V in some arbitrary direction will be enough. Now, if you consider equation 2 and differentiate equation 2 with respect to time, so differentiating equation 2 with respect to time or with respect to t. So now you know that dr prime dt equal to dr dt ddt of vt. Now dr prime dt is the velocity v prime of a body, then this is the velocity v, and v is a constant, so v will come out. Derivative of t with respect to t is 1. So v prime equal to v minus capital V. What is meant is that if a body is having a velocity v prime as measured in the frame S prime, that you can express in terms of the velocity v as you measure from frame S of the same body. So according to S, the velocity is v. According to S prime, the velocity is v prime. S prime is moving with a velocity capital V. So v prime equal to v minus capital V. So this is known as classical velocity addition formula. Classical velocity addition formula. Of course, you can also write it the other way around. For example, instead of writing x prime equal to x minus vt, you can see that x equal to x prime plus vt. So this way you can define the transformation of coordinates from rest frame to the moving frame, or from the moving frame to the rest frame. Now we'll see from this information. Remember, these laws that we are writing, these are under classical physics regime. So we are not considering relativistic mechanics yet. So we are only formulating the transformation equation under the classical physics regime. Now, these transformations that you have just seen, the Galilean transformation, what about the Newton's laws of motion? What about the correctness of the Newton's laws of motion under Galilean transformation? That I can state as invariance of Newton's law. So now you know that we have got two frames of reference, S and S prime. S prime is moving with a velocity v. The origin is now O and O prime. And we already have the equations involving the transformation of coordinates. Let us assume that the Newton law is valid in frame S. And in this case, we'll consider the most popular form of the Newton law, that is Newton's second law. So let Newton's second law is valid in frame S. That means if I make a measurement of force which is coming out to be F on a body of mass m, which is moving with an acceleration a, I'm not giving the vector sign, but you know that F and A are vector quantities. So F equal to ma is the Newton's second law of motion, which is valid in frame S. Now the question is, now we know what are the transformation equation. Using the transformation equation, can we show that if I make a measurement F prime, if I make a measurement of F prime in the frame S prime of the same body whose mass is coming out to be m prime and it is found to be accelerating with A prime, whether I can write F prime equal to m prime into A prime. So whether I have the equivalent form, that is the Newton's second law is invariant or not. So in order to establish that, the first assumption or the first fact under classical physics regime is that the mass of a body will not change from frame to frame. So under classical physics regime, m will not vary from frame to frame. So that means if I have m of a body in frame S, if I make a measurement from S prime also, they should be same. So m equal to m prime. That is number one. Now, since you know that mass is invariant, whether you are making the measurement in S or S prime, now you assume that this force, which can be also of different form, but I consider that force is the pull on a spring balance. There can be other type of force also, but I am considering that the pull of due to a mass on a spring balance, that pull I am considering to be the force in this particular case. Now you know that the mass is remaining same under classical physics in two frames. So then the pull also, or that particular force, should also be remaining constant. So that means F is equal to F prime. Now just look at our velocity addition formula, which gives me that V prime equal to V minus capital small v prime equal to small v minus capital V. Now, if you do a derivative with respect to time, then you know that capital V is constant, so this will give me A prime equal to A. So you have M equal to M prime, F equal to F prime, and A equal to A prime. So if F is equal to MA, then we must have F prime equal to M prime A prime. So if Newton's second law is valid in S, then Newton's second law should also be valid in S prime. Now this is only for second law. Now the same thing can be extended to first law and third law also. Of course, we are not going to do it here, but I have just showed how the second law is valid, and we can generalize this conclusion that Newton's laws are invariant under Galilean transformation. Okay, so this is one important observation. Now, so far, you see that everything is fine with Newton's law. But yesterday I mentioned that towards the end of 19th century, certain inconsistencies have been found or have been observed. Now, what are those inconsistencies? In fact, the most significant inconsistency is related to the speed of light. So we'll consider now the most significant inconsistency of the Newtonian mechanics. So Galilean transformation and the speed of light. So just now we have found that the Newton's laws are valid under Galilean transformation, but all laws, as I said, maybe till 150 years after Newton, Newton's laws were considered to be everything. But then in 1880, so around 1860, not 1880, around in 1860s, around 1861, 1862, there was another scientist, Maxwell. He formulated the laws of electromagnetism, which are known as Maxwell's equation. Laws of electromagnetism, which are popularly known as Maxwell's equations. Actually, there are 4 Maxwell equations, but if you combine these 4 equations, what you will find that if I consider that the electric field expression is E, in a certain frame of reference, the electric field is defined as E, then the second derivative of time of E is expressed as mu naught epsilon naught. I am considering that the medium is, the frame of reference is in free space, so there is nothing, it is vacuum. So under that assumption, the electric field behaves in such a way that the time derivative, the second time derivative of electric field is equal to mu naught epsilon naught. Probably you are familiar with the del square operator. This is the second derivative with respect to the space coordinate. So del square E. So this is the expression that is coming out from the Maxwell equation, and it is found that this expression mu naught epsilon naught is actually equal to 1 upon c squared. So 1 upon c squared del square E. The meaning is that in vacuum, the speed of light is coming out to be 1 upon mu naught epsilon naught. So if we are making measurement of electric field in a medium where the medium has got property defined by mu naught epsilon naught, in case you do not know, mu naught is the permeability and epsilon naught is the permittivity of free space. The formula also holds for some medium where the permeability and permittivity are different. So in that case, in a medium where the permeability is mu and permittivity will be epsilon, the velocity of light will be 1 upon square root mu epsilon. But let's consider that we are considering that the frame of reference where the measurement electric field is measured is there is air, there is vacuum only, and in that frame the velocity of light is found to be 1 upon square root of mu naught epsilon naught. Now mu naught epsilon naught is the property of the medium, and the property of the medium will not get affected, will not change depending on the speed, direction of light. So if the light is traveling upward, downward, left, right, whatever is the direction, the velocity should remain constant because it depends on the property of the medium. So according to Maxwell equation, velocity or speed of light, velocity of light is same in all directions. That is according to Maxwell equation, that the velocity should be same in all directions, but whether it will be true under Galilean transformation. Now here will come one very important inconsistency of the classical mechanics or the Newtonian mechanics. You can see, if I take the example of again my frames of references, S and S prime is moving with a speed v. Now you know that according to velocity addition formula, if something is moving, let's say in frame S with a velocity v, the same thing will be seen as moving with velocity v prime, and the two velocities are not same. V and v prime are not same. Now consider this case that light which is traveling, let's say a beam of light is traveling from left to right. And if we assume that Maxwell equations are valid in frame S, then in frame S, the velocity of light will be c. But you are making the measurement in frame S prime. So from S prime, you will consider that in frame S prime, the velocity of light will be c minus v. If the beam is moving from right to left, and since the Maxwell's equation is valid in frame S, so the velocity will be again bc. Because whether it is moving left or right, the velocity should remain constant. Now the same velocity of light, if you measure from S prime, you will, according to velocity addition formula, classical velocity addition formula, you will find the velocity to be c plus v. So the same beam of light, in one case you are finding the velocity to be c minus v, in the other case you are finding it to be c plus v, which according to Maxwell equation should have been constant. But you cannot have light traveling in one medium, but the light is having one velocity when it is propagating left to right, it is having another velocity when it is propagating right to left. It means the Maxwell equation can be valid only in frame S, it cannot be valid in frame S prime. That is as per the classical physics regime. Means classical physics is not able to explain the validity of the Maxwell's equation. It is establishing the validity of Newtonian law, but it is not able to establish the validity of Maxwell equation. So something has to be wrong. Either Maxwell equation is wrong, that some other terminology should be there, or something is missing in the way we are writing the Galilean transformation equation. So this was the most important inconsistency, which was eventually answered by Einstein. Now, what are the explanations those were coming? The explanation those were coming because you see that Newtonian laws were there for more than 200 years, and they were able to explain so many different phenomena, and that led to so many discoveries. So it was very difficult to imagine that something is inadequate in Newtonian law. So different theories were formulated, different theories were proposed. One such theory was that there is a medium called ether. There is a medium called ether, and light propagates with the velocity of c only in ether. So there is a frame of reference attached to ether. If you are measuring the velocity of light in ether, then you will see that velocity of light is c, but all other frames of references are moving with respect to ether, so you will not find the velocity of light to be c. So if you are not making the measurement in ether frame, then you will not find velocity of light to be c. So depending on the direction the beam of light is traveling, just like we have seen here, of course, if the light is traveling in this direction, then since there is no relative motion between S and S prime, we would have found the velocity to be c only. So it very much depends on in which direction light is traveling in order to find out what is the velocity in another frame. So what was proposed in the ether theory, that if the light is traveling in the ether medium, then it doesn't matter in which direction light is traveling, so it will be always c. But it will be having a different velocity if you are making in another frame. But that is only a proposal. In order to see whether that proposal is valid or not, you have to perform experiment. And I told yesterday that physics is an experimental science. I can propose anything. I can predict anything. but that prediction has to be validated by experiment, which I often say measurements. So measurement means an experimental determination of a particular quantity. So the velocity of light has to be determined in an experiment in order to tell that yes, there is a ether medium, and velocity of light is saying in all directions only in ether medium. So one such experiment which was performed was the Michelson-Morley experiment. So we'll discuss Michelson-Morley experiments in the next class. So in Michelson-Morley experiment, actually Michelson, and later on he was assisted by Morley, they tried to measure the change in the velocity of light. Now you see that for different frame of reference or different speed, the velocity should be different. So this part we will take up in the next class. I have only, so its time is up. You will have questions. I'll look at those questions, and I'm planning to have a discussion session on Friday, short discussion session. I'll send you a mail in this regard. I'll send a message in this regard. So you please check the Teams chat box. There I will send a message, and I will if you have some doubts, and I'll take up these questions also in that discussion session. So we'll stop here.